Okay. So today we're talking about kinetic and potential energy. And we can, right. Would you rather get hit by a Zamboni that weighs, has a mass of 505,148 kilograms, moving at 2 meters per second, or a 0.03 kilogram paintball moving at 85 meters per second? So we're going to revisit this question again at the end. All right. So energy can be defined in two ways. We can say that it has the ability to cause change. So maybe the change in an object's shape or the change in an object's motion. And another way we could talk about it is the ability to do work. And we're going to talk about the definition of work in another slide. There are lots of different types of energy: light energy, electrical energy, the chemical energy trapped in the bonds between atoms in a molecule, like those created during photosynthesis in glucose, thermal energy, nuclear energy, right? So in the center of a star, a huge amount of energy is used to compress together protons to create different types of elements. And the energy that was used to create those attractive forces between the protons can be released when we break them, like let's say through the use of a nuclear bomb or a nuclear power plant. Potential energy, and we have several slides to talk about potential energy, and then also kinetic energy, which we'll be talking about more in a second. All right, work. So when we talk about work in science, is a very different form of the use of the word work. We talk about work being done on an object, and that work is not the same thing as effort, right? So in real life, we use the word work like, oh, that sounds like a lot of work. Or really what you're trying to say is that sounds like a lot of effort, which is different from work in the sense of that we use it in science. So in science, we can define it as when a force causes displacement. So displacement is basically when an object moves from one point to another, right? That is its displacement. In order for work to be done, all three of the following must be true. A force must be applied to an object, the object must move, and the object must move in the direction of the force, which all sounds sort of obvious, but here's a couple of examples that maybe make it a little less obvious. Here I have a guy pushing on a really heavy box and the box is not moving. He's pushing really hard, he's sweating, his arms are getting tired, his muscles are getting weak. The box is not moving. Is work being done on the box? So you must ask yourself, is he applying a force to the box? Yes. Is the box moving? No. So therefore, work is not being done on the box. No movement, no work. This image shows someone picking up a box. So in this case, a force is being applied to the object in the upward direction. The box is moving and it is moving in the direction of the force. So work is being done on the box. Lastly, this example, man is carrying a box and he's walking with the box in this direction. Is work being done on the box? And the answer is no. And the reason why is because he is applying a force in the upward direction to the box, but the box is moving in the forward direction as he's walking. And so the force, the box is not moving in the direction of the force. So he is not doing work on the box. He did work on the box when he picked it up, but now that he's carrying it and moving forward, he's no longer doing work on the box. Okay, so that's work. Okay, so for this one, we're going to be talking about the SI unit for energy or work. It's the same, it's the joule. And we can define a joule as the amount of energy needed to apply a 1 Newton force over a distance of 1 meter. So you can see that we have been layering the units that we've been learning, right? We learned a Newton is equal to the amount of force necessary to move a 1 kilogram object at an acceleration of 1 meter per second squared. And now we're going to be talking about how that Newton fits into the idea of a joule. So a joule, again, is the amount of energy needed to apply a 1 Newton force over a distance of 1 meter. So if I take this Newton right here and I replace it with this kilogram meter per second squared and stick it in here, it looks like this. 1 kilogram meter per second squared times a meter. And when I multiply this meter times this meter, I get this unit, which is 1 kilogram meter square over second squared. So this right here is equal to a joule. And you'll see when we start doing some math that your units are going to come out like this. And when they do, then you get to replace them with a joule. So it looks scary and intimidating, but I promise it's not. It's simple. All right, law of conservation of energy, much like law of conservation of matter, which we've already covered this year, states that energy cannot be created or destroyed, right? But it can be transferred or transformed. So transferred means maybe transferred from one object to another, like as in this pendulum or this Newton's cradle. Or like this one, heat energy being transferred to the pan, which is then transferred to the food inside so that it can be cooked. Or it can be transformed from one type of energy to another. So the energy trapped in chemical bonds inside a battery can be transformed into light energy. Light energy from the sun can be transformed into chemical energy during photosynthesis. Electrical energy can be transformed into heat energy to cook your food and so on. All right, so potential energy is basically just stored energy. And there are lots of different types of potential energy. We're going to spend some time on the next slide talking about gravitational potential energy. Elastic energy is the amount of energy stored in an object that maybe has been stretched or compressed, like a rubber band. Chemical energy, energy stored in the bonds between atoms in a molecule. Nuclear energy, we kind of already talked about that. It's the energy stored in the nucleus of an atom. And then I just had a couple of pictures. All right, so let's talk about gravitational potential energy. Gravitational potential energy is the energy that an object has due to its position above the Earth, right? So it's up high, and it took some energy to get it up there. So whatever amount of energy it took to get it up there is the amount of energy it's going to be releasing, if we're ignoring things like friction, as it goes down. So that's about, so when we get the skier up here, if they have two different masses, the one with the mass that's greater is going to have more gravitational potential energy. And the same is true for our height, right? So height and mass are both factors, as well as acceleration due to gravity. So when we look at the equation, which we're not going to be calculating for this class, it's mass times gravity, which is the acceleration due to gravity, times height, can tell you how much gravitational potential energy an object has. And this kind of makes sense, right? If you were to drop something on your foot that had a really large mass, it would hurt more because it has more kinetic energy when it hits your foot. Also, if you dropped it from a higher height onto your foot, it would hurt more because it has more kinetic energy as it's falling because it had more kinetic energy before it fell. Okay. Kinetic energy is basically the energy of movement. And the amount of energy that an object has, kinetic energy that an object has, is going to be dependent on its velocity. So think about a very small bullet has a really high velocity. And so when it hits an object, it's got a tremendous amount of kinetic energy. Similarly, objects with a really high mass also have a lot of kinetic energy. So think about like a car crash, right? Some object with a really large mass colliding with something else. There's a lot of kinetic energy in that impact. All right, so energy that is kinetic and potential is sort of transforming from one to the other all the time. So as the bicycle goes up the hill, it's gaining potential energy because it's getting higher and higher and higher. And as it goes down the hill, it's losing potential energy, but it's gaining kinetic energy because it's going faster, faster, faster as it goes down the hill. So energy can be transforming from potential to kinetic all the time, back and forth. All right, calculating kinetic energy. So the formula that we're going to use for this is kinetic energy is equal to 1/2 the mass times the velocity squared. Okay, so the half is in there for every problem because it's part of the formula. And then the mass and the velocity are the two values that you're going to be given in the word problem to solve for kinetic energy, which, as a reminder, the SI unit for this is a joule. So let's do a practice problem. We have a 4 kilogram ball rolling at a velocity of 2 meters per second, and we want to know what is its kinetic energy. So we have our unit conversion, right? A joule is equal to 1 kilogram times a meter squared over a second squared. And here's our formula. So Dilpsau steps require us to do a drawing. So here's my drawing. And I've listed out my variables, which I have color coded to sort of match my formula. So you can see where the values are getting plugged in. So now I have my formula, I can go ahead and plug in my known values. So I have the mass and the velocity, which is going to be squared. And here's my 1/2. All right, so I color coded it. So yellow plus blue makes green. If I multiply my 1/2 times 4, I get 2 kilograms. And then I square my 2 meters per second. And when I do that, I get 4 meters squared over seconds squared. So this is where I'm at now. When I multiply this 2 times this 4, I get 8 kilogram meters squared over seconds squared. And remember, when we see kilograms squared over kilograms meters squared over seconds squared, just like this, that means that my answer is going to be in joules. So my correct answer is 8 joules. All right, so back to the end. Would you rather get hit by this tremendously large Zamboni moving at 2 meters per second, or this very tiny paintball moving at 85 meters per second? So if we use the kinetic energy formula, and you're welcome to pause this video now and do that, you will see that the amount of kinetic energy in our Zamboni is 10,296 joules, while the amount of kinetic energy in our paintball is only 108 joules. So a great deal more kinetic energy in our fairly, or at least relatively slow moving Zamboni. Keep in mind, 2 meters per second is actually pretty fast. If you think about that, that's about a span of 6 feet in 1 second. That's probably the fastest Zamboni I've ever seen. So, all right, if you have questions, please let me know.